So in this video, what we're going to be looking at is we're going to be looking at exponential growth problems. And specifically, we're going to be looking at how to deal with like these, kind of basic bacterial culture problems, or problems where we basically have a population. It's going to be growing at an exponential rate. How do we deal with those from both a calculus perspective and also from an algebra? So let's say that we have this problem. A bacterial culture contains 200 cells initially and grows at a rate proportional to its size. After half an hour, the population is increased to 60 cells, 360 cells. Find the number of bacteria after t hours. So the first thing that we need is we actually need an equation that kind of fits that differential equation that we set up inside a lecture. All right, and so our equation is going to end up being, we'll call it P of t, that's the population after time t, is going to equal P naught, our initial population, e to the kt. Okay, P of t is the population at time t. P naught is our initial population, which in this case is going to end up being 200 cells. K is our growth rate, which is oftentimes the thing that we're going to have to solve for. And then T, as always, is going to be time. Okay, so what I'm going to do is I'm going to utilize some algebra in order to kind of solve this problem or actually define this function. So what I know a couple of things. One is that P naught, okay, is equal to 200, and P of 0.5 after half an hour is going to equal 360 cells. It's 360. So I'm going to use that information in order to find this function. So P of t is going to end up equaling 200 e to the kt. So I just substitute there. And then I know that P of 0.5 is going to end up equaling 200 e to the 0.5t, or e to the 0.5k, excuse me, or k times 0.5, because t is 0.5 in that case. So now I'm going to actually utilize this, and that equals 360. Now I'm just going to do some algebra. So I've got e to the k times 0.5 equals 360 divided by 200. So then that means that e to the k times 0.5 is going to equal 1.8. Then I'm going to take the natural log of both sides. I'm going to let natural log of e to the k times 0.5 is going to equal natural log of 1.8. And so what that does is that I'm going to then pull out k times 0.5, and natural log of e becomes a 1. So this is 0.5 k is going to equal, let's just keep it at the natural log of 1.8. Finally, k, our growth rate, is going to end up equaling the natural log of 1.8 times 0.5. Pardon me, divided by 0.5. And so k will end up equaling 1.17557. Okay? Since k is greater than 1, that tells me that what we're doing is growth. Right? Whenever k is greater than 1, we get growth. Now, our function, P of t, is going to end up equaling 200, our initial rate, e to the 1.17557t. Now, we actually have an alternative way of writing this. We can also write this as P of t is going to equal 200, and then I'm going to take e to the 1.17557, and that's to the t power. Okay, just utilizing some rules of exponents. And what that allows me to do is it allows me to transform this into an actual function without its e, okay, into a different form. Plugging that into my calculator, I end up with P of t is going to equal 200 times, and this will be 3.24 to the t. Either one of these is actually the function. We can actually write it either way, or actually all three of those ways are ways of writing that particular function. Okay, so basically what we'll do is we're going to actually utilize this standard function, P naught e to the kt, okay, and we'll plug in the values, the information that we're given. Oftentimes that'll be an initial value, P naught, and a value at a particular time, okay, and then we've got some algebra that we're going to end up doing to allow us to find our function. And that completes finding the number of bacteria after t hours. What about if we want to find a particular number after a particular set number of hours? if we want to find the number of bacteria after, say, for example, 4 hours, all I've got to do is I've got to find P of 4. So P of 4, I'm going to use that second equation, 200 times 3.24 to the 4th power, and that'll end up equaling 22,039.6276. 6276 bacteria. Okay, so all we've got a function, and that function actually allows us to solve for the number of bacteria after a certain number of hours. We're just going to plug in T. What if I want to find the rate of growth for the bacteria after 4 hours? Okay, so one of the things that I would do there is I want to get that it's a rate of growth, right? So that means that I'm going to have to take the derivative. So P of T, okay, is going to equal 200 times 3.24 to the T. The derivative, P prime of T, okay, now that we've done this quite a lot, is going to be the natural log of 3.24 times 200 times 3.24 to the T. So that's actually then going to be just equal to, well, now we want to find P of 4, or P prime of 4, the rate of growth for the bacteria after 4 hours. So that's P prime of 4, and that'll equal then natural log of 3.24 times 200 times 3.24 to the 4. Well, we already know actually what this piece is right here. We just did it, right? It's going to be that. So we're going to actually end up with ln of 3.24 times 22,039.6276. Okay? And that ends up equaling 25,909.12502 bacteria per hour, right? Because what we're looking at is a rate of change. So again, we've got a rate of change. It's a rate of growth. So consequently, that means take the derivative. Okay, anytime you're looking for a rate of growth, you want to take the derivative, and that's exactly what we ended up doing right here. Okay. Now, finally, what if we want to find out how many bacteria actually happen to be, or at what time does a bacteria hit a particular culture? So let's see if at what time will the bacteria actually reach 10,000? So in this case, now that means that P of T equals 10,000. So we'll have 10,000 equals 200 to the 3.24 T. Okay. So I end up with 10,000 divided by 200. And that'll be 50. So we end up with 50 equals 3.24 to the T. And then we'll take the natural log of 50. That'll equal the natural log of 3.24 to the T. And what we know is that we can actually pull out the T. So this is going to be T ln of 3.24. And so there's ln of 50. So T will equal the natural log of 50 divided by the natural log of 3.24. So T, in this case, when we plug that into our calculator, is going to end up being 3.19668 years. All right. So it's just like working with a function, right? If you want, P of T is going to end up being a number of bacterium. So we know that we're going to plug in 10,000 as what P of T is, and we're going to have to solve for T. Key thing here is to remember, how do we do that utilizing logarithms, okay? Because exponential growth really does require the use of logarithms as well. Okay, so this finishes the lecture.